2, which is just a number, right? Which is just a number. See, that one you can't get by just looking, right? You can't just look at that, oh, it's natural log of 2, right? You have to actually, well, maybe you can, but, you know. Understood? All right, so would you have trouble with this integral? You would? If you distributed the negative through, what's the antiderivative of e to the x? Itself, right? Here, you would have to be a little bit careful. The antiderivative of e to the negative x. What's the antiderivative of e to the negative x? I'm going to show it because that comes up a lot in like differential equations and stuff. The antiderivative of e to the negative x, that will be something you have to do at some point here. That's just negative e to the negative x plus some constant. Right? You have a little bit of chain rule you have to account for. There's a negative in front of that, so you have to put a negative out front. All right, I'm ready to go into 7.2. I think we've exhausted this idea enough.
You should go back to the bonus.
Oh, the bonus, you want to write it down?
Yeah.
Here, you can take a picture too if you want. But it's $5 for the picture. All right, there you go. Is that big enough?
Yes.
Okay.
Assuming you got that from Real Steel, the movie.
The what movie?
Real Steel.
Mm-mm. Yeah, I'm not sure. Does he charge? Someone charges people?
Yeah, he
Oh.
wanted a cake for the picture. He
Oh.
said for $5.
Yeah, no, I've never seen that. All right, we ready? We're going to move on. Whoa, what happened? All right, I showed you all this in the very beginning of the class. Like one of our first days, I actually showed you this little animation. We've actually reached this point now. We're now going to talk about chapter 7, section 2. (7.2) solids of revolution. And some more stuff. There's more stuff in this section, but really this section is about this idea of what we call solids of revolution. So what we did in 7.1 is we said, all right, if we've got two curves, we can find the area between them. And so like, for example, if we had two curves like this, the blue is a function of x, the red is a function of x, right? So if we want to find this area, we would use vertical rectangles. And so you all see my little vertical rectangle there? Whoa, shit. My vertical rectangle, we imagine that rectangle, moves throughout that, and we add up all those areas and we get our total area, right? But the integral, right? The integral is just a tool. It's something we use to add things up. What's in the integral, right? The integrand is the most important thing. The integrand for us has been, like length times width to give us the area of a rectangle. But what's in there can be anything you want. It just needs to have some sort of meaning to it. So look at this picture here, and what we're going to do is we're going to say, what would happen if we took that region, I need my glasses. What would happen if we took this region and where is it? Took that entire region and we wrapped it around the x-axis. Okay, what do I mean? Take that region, we look at it from the side, like in a three-dimensional space. If we were to wrap that region around the x-axis, just like that, we would get a solid, wouldn't we? We'd get this solid object. Now you might be like, well, why would you want to do that? Well, don't worry about the why. Just like, could we just at least comprehend that idea of taking that region and wrapping it around the x-axis and getting that weird shape? And then the question is, what is the volume of that shape, right? What is the volume of that? Seem like a reasonable question? Okay, so the way we attack that, even though it looks like that's going to be really hard to figure out what that volume is, the way we attack it is we back this up. Okay, let's go back. And we go back to this picture with this rectangle, and we say, let's just see what would happen if we wrap just that one rectangle around the x-axis. Then I would get a shape that looked like this, right? And that's a pretty nice geometric shape. Like, we should be able to figure out the volume of that piece, right? And then, if I can find the volume for that, imagine moving it around, right? If I move it, it's going to change shape. Like, if I move it way over here, what happened there? It's like it got smaller, right? Like a smaller, but it now has a hole in the inside, right? When I move that rectangle somewhere else, like more towards the middle, it gets really big, and the hole in the middle is actually kind of vanishing away, isn't it? So just like we had before, when we had this idea of just finding a formula for the area of the rectangles and then just sliding the rectangle across by using the integral to add them up, we're going to do the same thing. We need to find a general formula for the volume of that shape, and then once we have a general formula for that shape, we will use the integral to add them all up, and that should give us the volume of the whole thing. Right? Do you buy that? For now? I mean, you kind of sold on the idea at least. The integral is a tool that adds things up. What do we want to add up? The volume of a bunch of these. What do we call these things? What do you think we call that? We call it a washer. Okay? That's what it's called, a washer. What'd you call it? Donut? Donut, yeah. It's more of a washer than a donut, but I can see how you could say donut. So this method that we're doing right now is called the method of washers. All right? And now I gave you this nice color handout today. You want a copy? Anyone else need a copy? These were $3. $3? No. Here you go. So look at the very top of this, solids of revolution, right? That's what we're talking about. Method of washers. Students always ask me, are we going to be able to use this on the test? And my answer is usually no, okay? This is a learning tool. It is not something that you're going to use for the test. All right, so the method of washers is the first thing we're going to do. And I put here next to that, rectangle is orthogonal to the axis of rotation. So that's a new word for you, orthogonal. If you don't know what that word means, it just means perpendicular, all right? So notice here, if I go back, we're rotating around the x-axis, aren't we? We're rotating around that x-axis, that's looking at it straight on. Do you all see that rectangle I had in there, right? Do you see that it is perpendicular to the x-axis? Yes? When you have that, okay, then we will follow this procedure. And then right there in this red box, right at the top, it says volume. See where it says V equals pi integral a to b r subscript 0 squared minus r subscript I squared dx. See that? Okay, that's what we're going to get to. I need to convince you of that formula. But at the end of the day, that's the formula. You just need to know what all those little pieces mean. All right, so y'all happy with that? At least the idea? Okay, so let's see if we can't generate the formula, get an idea here of how we're going to do this. So the first thing to motivate this, you know what, there's no reason for me not to have that up there. What I want to do is do a little recap of some geometry, some things that we have to all agree with, okay? Something we have to agree with. Let's say that I give you a right cylinder. We all need to agree with what the volume of this is. Now, you would have to be provided the radius, okay, r, and you would have to be provided the height of this, h. And then there's a formula, you could look it up, right? But the formula for this is volume equals pi r squared times h. All that's saying, if you recognize pi r squared, that's the area of that circle. And then what you're doing is you're multiplying that times the height, which is like the depth of the solid. So it's just like the area multiplied through times the height. Got it? Everyone agree with that? Understand it? Yes? So if I change this shape like this, is that still a right cylinder? It's just flat and very wide, right? But it's the same formula. If you give me the distance from here to here, call that R, and then distance from here to here, call that H. It's the same formula, yes? Okay. What if I gave you that shape, but I turned it on its side like this? And I told you that the radius goes from here to here, and then I told you that this from here to here is your height. Same formula? Same formula, right? There's no difference. So do you see, I'm trying to build up to this right here. I'm trying to build up to a washer. We all agree that if you're given a right cylinder, the volume of it is pi times the radius squared times the height. The radius is distance from the center to the outer edge. The height is just how thick it is, right? If we're looking at this picture. Do you see how this is all going to tie in? Like thickness is going to be dx and all that? Okay. We need one more thing. That thing has a hole in it, right? Sometimes it has a hole, sometimes it doesn't. So let's talk about a cylinder that has a hole in it instead of this. So let's say I give you a cylinder, looks like this. But now I come in here and I burrow out a circle right down the center, right? Right, like that. What would be the volume of that? Well, I would have to give you two different radii, right? Two different radii. So the distance, let's call the distance from the center to the outer one. I'm going to use a different notation. I'm going to do capital R-O. That's the radius of the outer one. Yeah? And then the one on the inside, that little smaller one, I'm going to call that the radius of the inner. And then from here to here, wouldn't the height be the same for both of them? Yes? Okay, that would be height. So what would be the volume? How could we find the volume of this? Well, one thing you could do is just think of it this way. You're taking the solid black one, you're finding the volume of that, and you're subtracting from that the volume of the smaller one, right? That's really what you're doing. So what would be the volume of the black one? Pi times RO squared times height. Do you all agree that that's the black one, right? The black one by itself. Okay, and then I subtract from that the volume of that one. Pi times the inner radius squared, right? Times H. That would be the red one. Yeah? So if I want the volume of this, what I do is I take the volume of that, I subtract the volume of that, and that should be my answer. Now, that expression right there, they have things in common, don't they? They both have a pi, and they both have a what? H. So I can factor out a pi h, and I'll be left with RO squared minus RI squared, right? Like that. Now that's a formula. I'm going to need that, right? Somebody gives me a cylinder that has an outer radius and an inner radius. The inner radius has been taken away, right? And we have a height, then that should be my formula. Questions there? I want to do one more thing before we get to the problem. It's the same exact picture I just drew. I'm going to draw it a different way. If I turn that on its side and make it like this, right? And then I come and I cut out a piece here. That's terrible. I'm not happy with that. But do you get the idea? That's that picture right there. From the center out, that's my RO. From the center to this piece right there, that's my RN. And then this right here to here, that's my H. Same formula, isn't it? So all I did was turned it on its sides and stretched it out and flattened it, made it thin. Okay? All right, so here we go. Let's back this bad boy up right here. So I've got this region, right? I've got this region bounded by two curves. And I want to wrap that whole region around the x-axis, and I want to find the volume. So what I'm going to do first is I'm going to find the volume of just one of these, right? Just one slice, one rectangle, wrap it around, and find its volume. So look at your sheet here. I'm going to bring up the sheet I just gave you. Where did I put it? Chapter 7. All right, let's see if we can do it this way. All right, so what we're going to do is we are going to take that rectangle, right, and we're going to wrap it around an axis. So there's my rectangle. I drew it over here on the side. Here's my rectangle. Here's the blue curve on top. Here's the green curve on the bottom. Now, if I wrap that around this purple line, I will get something that looks like this, right? This washer. And the question is, what's the outer radius, right? What's the distance from that axis of rotation to that top edge of the rectangle? And what's the distance from the axis of rotation to the bottom edge? Well, it depends. It depends. I mean, this should be the top function though, right? Whatever this f of x is, right? That should be f of x. That distance should be f of x, and this distance should be g of x. If the axis of rotation is the x-axis. It's not always going to be. That's why this is a general formula. But I want you to see from this right now that this distance right here, right, is just distance from the axis of rotation to that top edge, and this distance right here is the axis of rotation to that bottom edge. So let's do a specific example, all right, because this will all come together, I think, when we see a real example next to it. We'll do something very simple. Let's say we take, let's see, find the volume of solid formed by rotating the region, I'm making this up, y equals, let's do x, y equals x squared with x greater than or equal to 0 about the x-axis. These problems are like almost like little word problems every time you see them because there's a lot of information that has to be conveyed. So we want to find the volume of the solid that's formed when we rotate this region bounded by these things or given these conditions around the x-axis. So I'm first going to just draw this. Okay, my red one is y equals x. You know what? Let me do it the other way around so it'll match my picture up here. Let's make this the blue one. This is my blue one. Y equals x, we all know, is just the diagonal, right? Like that. Y equals x. And then y equals x squared. Right, goes like this. X greater than or equal to 0. Just make sure we're only looking over here, okay? Even though there actually is no region back here. I didn't need that, but I put it there just so we could focus our attention this way. All right, we want to take, do y'all see the region bounded by both of them? Right? We want to take this region and we want to wrap it around the x-axis, right? We want to wrap that region around the x-axis. So I'm going to do something else here. This is the first time you're going to see me do this. I don't think they have purple markers over there. Thought I had a purple. Let me see if they have a purple. Go hang tight for 10 seconds. Yeah, ow. Yeah, no purples. All right, so I need to be very explicit here. We're going around the x-axis, right? So I'm going to put a dotted line through the x-axis like this, okay? And I'm going to draw this little like curved arrow that goes like this. And that's telling you the axis of rotation. So I'm rotating this region around that x-axis. I'm trying to find the volume of that solid. So what I can do is I can imagine that I have rectangles in here, right? Vertical rectangles. I'm using vertical rectangles because these are functions of x, right? So vertical makes the most sense. My rectangle is orthogonal or perpendicular to my axis of rotation, right? So I'm going to use this method of washers. Because when I wrap it, I'm going to get a washer, right? Okay, so let me see what that washer looks like over here. If I imagine taking this little rectangle over to the side, I know that I have my blue curve on top. I have my red curve on the bottom. I have my axis of rotation down here, which happens to be the x-axis as well, right? This happens to be the x-axis, which is good. And now what I need to do is I need to figure out when I wrap this, I'm going to come over here and do your best with this wrapping. I know I have a washer, right? And I know it has some sort of hole in it. Do you all see the rectangle in there that gets wrapped? Some people see it, some people don't. You're taking that rectangle and you're wrapping it around here and you're getting this like that, right? Questions? Y'all like my pictures? Good? All right, so what we need to do is we need to figure out the distance from here to here, which I call RO. And then this distance from here to here, which I call RI. The outer and inner radius. If I have that, then I have a formula, don't I? We just covered what the formula was, right? Pi, blah, 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 blah. So for us, in this problem, can you tell me what RO is, the outer radius? Can you tell me explicitly? Well, it's the distance from the blue to where? The x-axis. Well, isn't that just the function itself? Isn't that just, what's my blue function? Y equals x, right? That's y equals x. So that should just be x. And then what's my inner? Well, that's the distance from this axis of rotation to the red, but that's the same as this distance, which is just the red function, right? Which for us is x squared. So I know the outer and inner radius. The only thing I need now is the height, which for us, remember, height was the cylinder this way, but we turned it on its side and flattened it out. So our height is actually the thickness of the washer, which is the thickness of the rectangle, which is dx. So that thickness right here is dx. So do you all agree with this formula I have here in red? Wait a minute, there's more, isn't there? Yeah, no. So I'm going to put it up on the board. What would the volume of this one washer be? The volume of just this one. The volume of this, the volume would be pi, right? Pi, because remember the formula we just had, right? What was our formula? Pi h r0 minus ri, right? That was our generic formula that we had come up. So pi times h. What's h for us? dx times ro, x minus x squared, right? That would be the volume of just that one washer, right? Just the one washer. And then we bring out the big tool, right? The integral. The integral allows us to add up all of those washers together, to sum them up, to imagine making an infinite number of these rectangles in here and wrapping an infinite number of them and making an infinite number of washers, right? And then we're going to move from where? Here to here. Where? For us, it's from 0 to where? Where do they hit each other? 1, right? at 1. So all we have to do is integrate that formula from 0 to 1. And we have the total volume. So my final result here is not the volume of that slice. If I want the volume of the whole thing, the volume of the solid, right, will be the integral from 0 to 1 pi times dx times x minus x squared, right? That's basically saying I want to add those all up, right? Sum them up. But we can clean that up, can't we? Like, they both have, I mean, sorry, not they both have. Pi is a constant. So I can pull the pi out, right? Integral goes from 0 to 1. And then, don't we normally like put the dx in the back? It's just multiplication, though. There's your integral, right? Pull the pi out, pop the dx to the back. Can you do this integral? Yep. You get an answer. And that answer, numerically, is the volume of that solid.
Why aren't you squaring the
Oh, I didn't square them. Why didn't I square them? I'm glad you pointed. Why didn't anyone else say that? Okay. I knew I was having too good of a day. Like, I started out this day, felt like shit, and then I knew I was going to make a mistake somewhere. Okay, what am I missing? Someone pointed it out here. What's our formula? R squared, right? R squared. I forgot to put the squared in. When I wrote it down here, did I write it right? Pi h, and then I put RO minus R. I think I forgot the squareds here. Didn't I? Squared, squared. It's right there, but I, for some reason, forgot the squareds. But that makes a difference right here, right? Because I have to square these radius, the radii. Square that and square that. I better put it here too. We'll do another example since I screwed that one up. But at this, do you agree that that's doable now? I mean, it's just x squared and x to the fourth. You could integrate those? Yes? Do you understand the geometry? Because that's the most important thing, is the geometry of it.
Yes.
The RO, I put here on the side here. This is really, really important. I have to scroll over here. It's on your notes there. It says here that the RO, right? The RO, the outer radius, is the distance from the axis of rotation to the outer edge of the rectangle. From the axis of rotation to the outer edge. It is not always the distance from the x-axis to the rectangle, as you'll see. The inner is the distance from the axis of rotation to the inner edge of the rectangle. So here. So what I want to do to kind of motivate that is go back to this picture I had here, right? Where we had this thing. We said, okay, we're going to wrap this sucker around the x-axis, and that's going to give us some washer, and if we wrap all the washers together, we get that solid. Yeah? But nothing says my axis of rotation has to be the x-axis. It could be any axis. Like, there's that same region. I know they're small, but I want you to see them all together. Right? This is the x-axis, right? That's the x-axis, and we just did that. We could wrap this rectangle around the x-axis, or we could do a line somewhere below it. Like, instead of the x-axis, wrap it around a line way down here, or a line above it, below it or above it. If I wrap that rectangle around, are we going to get the same solid for each of those scenarios? We shouldn't. Let's see. Do you see me wrapping the rectangle around those three different axes? And do you see I get three completely different washers? And if I do the entire solids, I get three different solids, right? All of these solids have different volumes because the axis of rotation is in a different place. So what we need to be able to do is take any arbitrary region, wrap it around, of course, the x-axis, find its volume. Then I'm going to give you a line somewhere below it. You need to wrap it there and get a different answer. And then I'm going to give you some line above it. Okay? In this class, we will only wrap things around horizontal lines that are, well, horizontal, right? Here, below, or above. And then we will also do vertical lines. What happens if we wrap this region around a vertical line instead, like the y-axis? Or some line over here, or some line over there. Well, I'm going to show you that in a moment, right? We never in this class try and wrap around a line that's not horizontal or vertical. It can be done, it's much harder, but we don't do it in here.
And the problems, it's gonna tell you what it's gonna want to
It
do.
will tell you.
Like this one says about.
This one said about the x-axis, right? All right, so yeah, let's do that. How are we doing time-wise? Yeah, great. All right, so I would like to do another example. Leave this up here. See if I can do this without screwing it up. This is our formula. The volume using a method of washers, method of washers, is that the volume will be pi, the integral from A to B. A to B is the left and right limits of that region, right, of the outer radius squared, damn it, minus inner radius squared, all right, dx. All right, I want this problem again. The same problem that I just screwed up, we're going to do it again, but this time I want you to wrap it around y equals -4. So, continuing this, now find volume if rotated about y equals -4. It's the same region, right? This same region, but I want it wrapped around y equals -4 instead. So I'm going to draw again. Give yourself plenty of space to draw this. I'm going to go a little smaller, okay, than I just drew. Tell me if you have trouble seeing this. I know I'm only in the first quadrant. We had, this was y equals x. I'm thinking back in my career right now, if I've ever screwed that up before with the squared on that radius, and I don't think I've ever screwed that up in class. That's a first. It's first for everything. I am losing my touch. It's going. It's going. To me, that's a big screw up. This is the first time you're seeing it. I'm screwing the formula up. All right, so there we go, right? I look at it. I want to wrap this about the y-axis. Let me put my not y-axis, around y equals 4, which is y equals -4. I'm just all over the place now. Y equals -4 is down here, yes? So I want to wrap it around an axis down here. Okay? So here's my axis of rotation. Draw a little circle. On the exam, your next exam, I'm going to have you do this, right? And you don't even have to compute the integrals. You don't even have to find the volume at the end. Like, you don't have to actually get down to the numerical answers. You just have to get the right formula, the right integral set